Dear students, welcome back to the lecture series on solid state. In this session, we will discuss about close packing in crystals, that is the packing of structural units in crystals. There are different ways of packing of structural units in crystals, and we will see in detail all these types, particularly the hexagonal close packing and cubic close packing. The packing of the structural units, that is the atoms, ions or molecules in a crystalline lattice, determine the shape of the crystal. When we deal with the diagrams of different types of cubic lattices, especially simple cubic as you can see here, or a body centered cubic or a face centered cubic lattices, we represented them using very small spheres separated by some distances. So, we may feel that these spheres are separated by some long distances and there are lot of space in between them, but actually it is not so. The spheres, when I say spheres, that means they are the structural units. They can be either atoms, ions or molecules. Okay. For the timing, let's say they are spheres. We are considering them as rigid spheres. So, the space between these spheres is very less, as you can see here. Okay. The spheres or the structural units are very closely packed in any of the crystalline lattices such a way that there is minimum of empty space in between these structural units. As you can see here, whether it is a simple cubic or a body centered or a face centered, the atoms, ions or molecules which constitutes the structural units, they are very closely packed so that the empty space in between them is minimized. This is referred to as close packing of spheres in crystals. So, what is meant by close packing? The most efficient way to arrange the structural units, which are atoms or molecules or ions in a crystal lattice, to minimize the empty space is referred to as close packing of spheres in crystals. Now, why there is such a close packing or minimization of empty space? That is to have maximum possible attractive interactions so as to reach a state of lowest possible energy. A state of lowest possible energy means a state of maximum stability. Okay. So, in crystalline lattice, the structural units such as atoms, ions or molecules, which we consider as rigid spheres, are very closely packed to minimize the empty space. And why they are very closely packed? In order to have maximum possible attractive interactions. And when there is a maximum attractive interactions, they will reach a state of lowest energy. And a state of lowest energy means a state of maximum stability. And this is referred to as close packing or closest packing of spheres in crystals. Now, let us consider the close packing of spheres in one dimension. Okay. When we say spheres, we always deal with some metallic atoms or ions which are roughly spherical. Okay. That is why we are considering them as rigid spheres. So, here it is the close packing of spheres in one dimension. So, in one dimension, how can we arrange the spheres without any empty space? As you can see in this figure, all the spheres, all the adjacent spheres touch each other. Okay. Now, when we consider any sphere in the middle, you can see that it is in close contact with two other adjacent spheres. So, the number of equidistant nearest neighbors of a given structural unit in a crystal is known as the coordination number. When we consider the sphere marked here, you can see that there are two adjacent spheres which are in close contact, that is two nearest neighbors, equidistant nearest neighbors. So, what will be the coordination number of this sphere? The coordination number will be equal to 2. So, the coordination number is the number of equidistant nearest neighbors of a given structural unit in a crystal. So, when we consider the close packing of spheres in one dimension, the coordination number is equal to 2. In terms of three-dimensional packing, the above arrangement in a row constitute what is known as the edge in a crystal. So, this is the close packing of spheres in one dimension. Now, we will move on to the close packing of spheres in two dimensions. On the screen, you can see the close packing of sphere in a row, that is in one dimension. Now, when we add another row of spheres directly above the first row, you can see here that the second row of spheres are placed directly above the first row. Again, when we add a third row, it is again directly above the second row. So, if we mark the first layer as A, you can see that the second layer is the exact replica of the first layer. So, that can also be named as A. The third layer is also A. Okay. So, this kind of packing of spheres in two dimensions is referred to as the AAA type, and this is also known as square close packing. Consider a sphere in the middle row, okay, any middle sphere in the middle row. You can see that it is in close contact with 4 other spheres. So, if we connect these spheres, we can create a square, or the centers of these neighboring spheres are at the corners of the square. So, that is why this kind of arrangement is called a square close packing. Now, what will be the coordination number? When we consider the sphere, you can see that it is in contact with 4 neighboring spheres, close contact with the 4 neighboring spheres, and hence what will be the coordination number? The coordination number will be equal to 4. Okay. So, this is one kind of arrangement of spheres in 2 dimensions. So, in 2 dimensions, we have seen the arrangement of spheres. The new layers are added directly above the first layer or second layer, directly above the spheres of the first layer. So, all the layers are equivalent. So, they can be named AAA, etc. So, this kind of arrangement is called AAA type arrangement, or it is also known as square close packing. And why square close packing? Because if you consider any sphere in the middle of the layer, you can see that it is in close contact with 4 other spheres, and the centers of these spheres can lie on the corners of a square, and that is why this is also known as square close packing. and it will have a coordination number of 4. Now next we will see another kind of arrangement of spheres in 2 dimensions. So on the screen you can see a 1-dimensional row of spheres. Now if we add the second row of spheres into the depressions of the first layer. Okay. So depression means instead of placing the sphere directly above, the sphere is placed here. The second one is placed here. The third one here. Okay. So into the depressions of the first layer, we are going to place the second row of spheres. So this is how it looks like. Okay. Now when we want to add a third layer on this, that will be again onto the depressions of the second layer. Okay. So if I mark the first layer as A, the second row of spheres, you can see it is situating in the depressions of the first row. So it is not A, but we can name them as B. Again the next type into the depressions of the second row, but that will be equivalent to the first row of spheres. So again that will be A. So when the spheres are arranged in 2 dimensions like this, the sequence will be AB, AB, etc. Okay. So this is called hexagonal close packing or AB, AB type packing. Now why it is called a hexagonal close packing? Consider a sphere in the middle row. Okay. You can see that it is in close contact with 6 other spheres. The nearest equidistant neighbors, there will be 6 spheres around this central sphere. So if we connect them like this, you can see that the centers of these spheres lie at the corners of an octahedron. I am sorry, the centers of these spheres will lie at the corners of a hexagon, and that is why this is called a hexagonal close packing. So as you can see here, each sphere is surrounded by 6 adjacent spheres. So the coordination number will be equal to 6. And when we look in terms of 3 dimensions, the arrangement in a layer constitutes what is known as a plane in a crystal. Okay. So here we have seen the close packing of spheres in 2 dimensions. The first one was square close packing, in which the additional rows are placed directly above the below rows or the neighboring rows. So that is called AAA type packing. The second type is called the hexagonal close packing or ABAB type packing. Now the most efficient packing, which contributes to 60.4% of the available space, is achieved in this kind of arrangement, that is via hexagonal close packing. Okay. So you can see here that when the second row is placed in the depressions of the neighboring rows, that will be more efficient way of packing, and it will contribute to 60.4% of the available space. So that much space is occupied by the spheres, and that is called hexagonal close packing in 2 dimensions, also called ABAB type. So now we will move on to the close packing of spheres in 3 dimensions. So this refers to the close packing in 2 dimensions. Now 3 dimensions means we are going to add a few layers on top of this. So, this is the first layer. Now, when we add a second layer on the top of it, you can see that when the rows are arranged like this, still there will be some empty space in between, as you can see here. So, these are the empty spaces, and these empty spaces are also called voids, or they are also known as holes. So, voids or holes are the interstitial spaces or empty spaces formed in between these spheres. Okay. So, these are the empty spaces and these are also the empty spaces. Okay. Now, we are going to add the second layer of atoms or spheres on top of this. So, now let us see what happens. When we add the second layer of atoms into the depressions of the first layer. Okay. So, we have added atoms onto the depressions of the first layer. Why? Because that is the most efficient way of packing in 2 dimensions. So, we have added 2 more rows of spheres onto the top of the first layer. Now, again when we add these rows, still there are some empty spaces in between, as you can see here. So, all these are the voids or the empty spaces. Now, what happens when we add a third layer on the top of this? Okay. So, we have 2 layers. Let us mark them as this is the first layer, let it be A, and this is the second layer and let it be B. Okay. Now, we are going to add a third layer on top of it. So, we have seen that there are empty spaces in between. So, the spaces that is marked in white color triangular are empty spaces. Not only that, but these orange colored triangular holes, these are also empty spaces. So, all these are empty spaces formed by the close packing of the spheres. Now, what happens when we add a third layer on top of it? As you can see here, when we add a third layer onto these depressions, okay, the orange colored depressions that I marked in yellow, when we add the third layer onto these depressions, you can see that these spheres are placed vertically aligned above the first layer, or these spheres are placed directly above this first layer. So, this kind of arrangement is called hexagonal close packing, which is also referred to as HCP. Okay, hexagonal close packing. So, what is hexagonal close packing? We have one layer of spheres or atoms arranged. This is the second layer, which we denoted as B, which are placed onto the depressions of the first layer. Now, when we add a third layer on top of it, we have placed them onto these depressions which are marked here. So, when we place onto those depressions, these become aligned vertically above the first layer. Okay. So, such an arrangement is called hexagonal close packing, HCP. So, the 3-dimensional close packing arrangement of identical spheres in which the spheres of the alternate layers are vertically aligned is called hexagonal close packing, or it is also known as the ABABA type packing, because this first layer is A, the second layer is placed onto the depressions of the first layer, so that is named as B. Now, the third layer is again, it is vertically aligned over the first layer, so it is again equivalent to A. So, if we place a fourth layer above it, then that will be similar to that of the B layer. So, in that way, we will have a pattern like A, B, A, B, A, B, etc. So, such kind of arrangement is called hexagonal close packing or HCP arrangement in 3 dimensions, or it is also known as ABAB type sequence. Now, let us find out the coordination number in a hexagonal close packing. Okay. So, consider any sphere in the middle. So, let it be the sphere. You can see that it is surrounded by 6 spheres which are in close contact. Now, into the depressions of these spheres, we can place 3 other spheres as shown here. Okay. So, 3 can be placed on the top of this and 3 can be placed onto the bottom plane also. Okay. So, when we consider a central sphere, there will be 6 spheres. When we consider a central sphere, there will be 6 spheres around it plus 3 spheres on the top plus 3 spheres on the bottom. So, the coordination number will be equal to 12. Okay. Now, this corresponds to a hexagonal type of arrangement, as you can see here, resulting in a 6-fold axis of symmetry or C6 symmetry. So, hexagonal close packing is one of the most efficient ways of packing of spheres, in which the coordination number is 12 and having a C6 axis of symmetry. Metals like beryllium, magnesium, cobalt, zinc, cadmium, molybdenum, etc. exhibit hexagonal close packing in their crystals. Okay. So, we have seen a particular kind of arrangement of spheres or packing of spheres in 3 dimensions, and we named them hexagonal close packing. Now, let us see another type of arranging spheres onto the top layers. So, this is one layer. The second layer we created by placing the spheres onto the depressions of the first layer. So, let the first layer be A, the second layer be B. Now, when we add the third layer of spheres onto the depressions marked like this here, when we place the spheres onto these depressions, you can see that a new layer is created. It is not directly above these first layer orange colored spheres, nor it is directly placed over these white colored spheres, but instead they form a new layer. So, we may name them as C. Okay. So, the first layer is A. Onto the depressions of the first layer, we created another layer called B. Now, the third layer in hexagonal close packing, where we placed them? We placed directly above the first layer, right? They are vertically aligned according to the first layer. But here the third layer of spheres are placed into the depressions, but they are not directly above any of these two layers. So, these three spheres will form a new layer. Okay. Similarly, you can place the spheres like this. Okay. So, this kind of arrangement is called a cubic close packing or CCP, or this can also be called as ABC type packing in 3 dimensions. Now, if we add a fourth layer above it, so that will be directly above the first layer, equivalent to the A layer. The fifth layer will be equivalent to the B layer, and the sixth layer will be equivalent to the C layer. So, that pattern will repeat. So, that is why it is called an ABC type packing. Okay. So, here we have seen two different ways of arranging the spheres in 3 dimensions. The first one was hexagonal close packing, in which the third layer was vertically aligned over the first layer, which is called AB type. Now, here we have seen the third layer onto the depressions of the neighboring rows or neighboring layers, but they are not directly aligned over the lower layers, and it will create a new pattern called ABC, and this kind is called cubic close packing or CCP. So, the overall structure can be visualized as a cube where the atoms are located at each corners. In a cube, we have 8 corners. So, at each corners there will be spheres or atoms, and also in the center of each face. So, when atoms are present at the corners and also at the center of each face, then that will be identical to a face centered cubic packing or FCC packing. So, that means the cubic close packing CCP is also known as a face centered packing or FCC packing. Now, let us find out the coordination number in cubic close packing. So, when we consider a sphere in the center, you can see that it is surrounded by 6 spheres. So, when we add the other layers, there will be 3 spheres on the bottom plane, and on the top plane also there will be 3 spheres. So, again we have 6 plus 3 plus 3. So, that will contribute to a coordination number of 12. And in cubic close packing or face centered packing, the symmetry will be a C3 axis or 3-fold axis of symmetry. Metals like calcium, strontium, copper, silver, gold, etc. exhibit cubic close packing or face centered packing in their crystals. Now, let us compare the hexagonal close packing and cubic close packing. So, both kinds of arrangement, that is both HCP and CCP, are ways to arrange atoms in a crystal to achieve the maximum possible density. And these two kind of arrangements are the very efficient ways or most efficient ways to pack spheres, achieving a packing efficiency of 74%. A packing efficiency of 74% means that 74% of the volume is occupied by these spheres. So, leaving only 26% as empty spaces or voids. Both kind of packing, both HCP and CCP have a coordination number of 12, meaning each sphere is in contact with 12 other spheres. Now, let us see the difference in the stacking sequence. In HCP, as we have seen, it follows an AB type stacking sequence where the third layer is directly above the first layer. Whereas in CCP, it follows an ABC type stacking sequence where the third layer is shifted and it is completely different from the first 2 layers. The shape of the unit cell. HCP has a hexagonal unit cell with a 6-fold axis of symmetry, whereas in cubic close packing, It is a face-centered cubic unit cell with a C3 or three-fold axis of symmetry. So, in short, while both the hexagonal close packing and cubic close packing achieve the same high packing efficiency and coordination number, their underlying structures and unit cells differ due to the way their layers of atoms are stacked. So, today we have discussed two types of packing of spheres in 3 dimensions, namely hexagonal close packing and cubic close packing, and we have detailed discussion on the types of arrangement. So, now let us discuss a few questions based on today's topic. Hexagonal close packed arrangement of ions is described as option A, ABC, ABA, option B, ABC, ABC, option C, AB, AB type, and option D, ABBA. So, we have seen that in an HCP arrangement, the third layer of atoms are vertically aligned over the first layer. So, that kind of arrangement is called an ABAB type arrangement. So, the answer is option C, ABAB type. Question number 2, which of the following has an HCP crystal structure? Option A, calcium, option B, copper, option C, silver, and option D, magnesium. And among these, magnesium adopts a HCP crystal structure. So, the correct option is option D, magnesium. Question number 3, the coordination number of a metal crystallizing in a hexagonal close packed structure is option A 4, option B 12, option C 8, and option D 6. So, we have seen that in an HCP structure, there will be 6 spheres around the central sphere, 3 on top of it and 3 below it. So, that will contribute to a coordination number of 12. So, the correct option is option B 12. Question number 4, the close packing represented by ABC pattern corresponds to. We have 4 options, and in our class we have seen that the pattern ABC refers to a face centered cubic packing, which is also known as cubic close packing, either CCP or FCC. Okay, so here it is given face centered cubic packing. So, the correct option is option B, FCC. And the last question, what will be the coordination number if the particles are arranged in one dimensional close packing? So, we have seen that in one dimensions the spheres are arranged in a single row. So, if you take any sphere that will be in close contact with 2 other spheres, so the coordination number will be 2. So, the correct option is option B 2. Okay. So, in the next class we will continue our discussion on the empty spaces or voids in these crystalline packing or close packing of spheres. Thank you.